Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Module 4. So in Module 4, we will talk about the binary numeral system and its application. Part 1. Okay, so here's the learning objectives of Module 4. Now, in Module 4, we're going to first talk about the decimal numeral system. Okay, now the decimal numeral system uses 10 symbols, and we normally use these 0, 1, 2, and all the way to 9 to represent each numbers in the decimal numeral system. And these symbols are also called Arabic numeral. So the decimal numeral system is also sometimes also called the base 10 system. Now, then the next one we're going to talk about is the binary numeral system, which is widely used in computer system. Okay, so the binary numeral system uses two symbols, 0 and a 1. Okay, and then with binary numeral system, we will introduce the 2's complement notation. So the 2's complement notation uses fixed number of bits to represent both the positive and negative values in the system without introducing the positive or negative sign. So typically, when you do the addition and the subtraction, we will introduce the sign like a positive, the plus, or negative. But using 2's complement notation, we can eliminate these, positive and negative sign. So the good thing about this is the addition in 2's complement notation will be pretty simple because both the addition and the subtraction will follow the same rule. Now, however, there's always a drawback with 2's complement notation. One of these is the overflow. Okay, so we will talk about this in Module 3. Now, lastly, we will introduce a new notation called the hexadecimal notation. Okay, so sometimes we use hex for short. Now, hex is a numeral system that uses 16 symbols. Okay, so we will use the symbols like a 1, 0, 1, 2, all the way to 9 to represent the first 10 numbers. Then, for number 10, we will use A, B for 11, C for 12, and D for 13, and E for 14, and F for 15. So that's total of 16 symbols. And that's the hexadecimal notation. Now, hex is widely used in digital electronics and computer engineering because hex is relatively short than the binary system. And also, hex is very easy to convert into a binary and vice versa. Okay, so let's talk about decimal or base 10 numeral system. The decimal numeral system uses 10 different symbols. We call these 10 different symbols digits to count numbers of given set in a consistent manner. Okay. Now, the most popular numeral systems are called Arabic numerals. Now, sometimes we also call these a Indo-Arabic numeral. Now, the Arabic numerals, as we know, and are the characters that were originally documented and used in ancient India. So it's first used in India, no later than 9th century. And then the Arabic numerals was later modified and transferred to Arabs, and from they were introduced to Europe in the 10th century, so as 1 century later. Okay, so let's talk about how the decimal numeral system works. Now, we're going to start our discussion by counting the numbers using the decimal numeral system. Okay, now let's start to count the number from zeros. Okay. So now we start the number 0, which basically means nothing, and then we want to add 1. Okay, so we count 1. And then we want to add 1 again on top of 1, so we get a 2. And add another 1, we got a 3. So we keep adding numbers on the existing number. So we got a 4, 5, 6, 7, 8, and a 9. Now we know that the decimal numeral system uses 10 symbols. Now here we have run out of symbols. So in order to count 1 more, then one way we can do is we add another symbols. But we are not going to do this. What we're going to do is we're going to add a new placeholder on the left and reset the value to 0. Now this new placeholder is called tens position. Okay, that's number 10, so tens position. Now the current position is called ones position. So then we're going to add a 1 to the tens position. So we got 1, 0. That's number 10, which is 1 more than the number 9. Okay, so then we can continue to count the number. Since we have free up one's position and set the one's position back to 0, so now we can increase the number in one's position. So then we can count the next number, 11, which is 1 more than 10, and then add another 1, we got a 2, and we continue to add the number until we reach 9 in one's position. Now the tens position is also still 1. Now we're running out of the symbols again in one's position. Now what are we going to do? We're going to reset one's position to 0 and add a 1 to tens position. Okay. Now since the tens position already has a 1, so then we are actually going to add a 1 on top of 1, so we got 2 in tens position. And then we can continue to count. So add a 1 in one's position and keep the tens position 2, and we can continue to do this until we reach to 9. Then we are running out of symbols again in one's position, and then we can reset to one's position to 0 and add a 1 to tens position. So this makes tens position 3. So we can keep counting like this, and then we're going to actually reach 40, 50, and until we reach 9 in tens position, and then we reset one's position to 1. So we can continue to count, right? 1, 9, 1, 9, 2, until we reach 9, 9. Now we reach another milestone because both one's position and tens position reaches 9. So both are reaching to the limit. So what we're going to do next? So we can reset 1's position to 0 and add a 1 to the 10th position. Now, since the 10th position has a 9 already, so the 10th position is also running out of symbols. So we have to reset the 10th position to 0, and then we're going to add another placeholder on left of the 10th position. We call these 100th position. Now the 100th position basically represent any number in 100th position represent 100. So we're going to add a 1 to the 100th position. So that is the number 100, which is 1 more than 99. So we can continue to count, right? So the 1 after 100 is 101. So we're going to increase the 1's position first, and until we are running out of symbol in symbols in 1's position, then we, add a 1 on the next position and reset the 1's position. So we can continue to do that. So that's the decimal numeral system. Okay. Now what's so good about decimal numeral system? Now the decimal numeral system allows us to, represent any numbers using only 10 symbols. So no matter how big the number going to be. Okay. We just simply adding more placeholder on the left. Now let's talk about, when we talk about decimal numeral system and the advantage of decimal numeral system, let's actually talk about another numeral system. So, okay, and then we just compare these two. Okay, so the other numeral system we're going to talk about is called Roman numeral. Now, if you have old clock or your grandpa's clock, so sometimes you're going to see these Roman numeral. Okay, so in Roman numeral, typically people use I. Sometimes we also call this alphabet. We use I to represent a 1. So we can write 2I to represent 2 and a 3I to represent a 3. What do you think the number 4 using Roman numeral? Are we going to add one more I? No, we are not going to do this. So basically we're going to introduce a new symbol. That's V. Now V is not 4. Okay, V actually represents 5. Now in Roman numeral, so we can represent 4 by combining the V and I. So we can actually put the V, which is 5, but we need to reduce 1, right? We need to subtract the 1. So that means we're going to put the I on the left, which means it's a 5 subtract 1, so which is a 4. Now for 6, so we're going to put the V and put the I on the right. Okay, 7 V I, and 8 V I. So now what about 9? Again, we're not going to add one more I's on the right. What we're going to do is we're going to introduce one more another symbol, which is X. So X basically represents 10, but for 9, so we need to subtract 1 from X, right? So 9 is this. Now 11 going to be XI. So we can keep doing this. Okay, so that's the Roman numeral. Now Roman numeral is good, if we try to represent a small number. But if we would try to represent a huge number like a 1 billion, it is a nightmare. So that's the reason why decimal numeral system is much better than the Roman numeral. The Roman numeral works for a small set of numbers. So now let's take a look at an example of the decimal numeral system. Now let's look at the number 256. Now this is actually called standard form or standard notation. So the 6 here is in ones position, as was discussed in the previous slide, and the 5 is in tens position, and 2 is in hundred position. So this means the number 6 basically represents just a 6, but the number 5, which is in tens position, actually represents 50, which is 10 times the number 5, and the 2 actually represent 200. Now we can also write the decimal number as an expanded form, so in which that we can write any number, decimal number, in terms of the sum of the numbers in different positions. So for 256, so we can write as 6 times 1, 5 times 10, as 5 is in tens position, and 2 times 100. Or we can write in the digital form. So it's just 2 times 100 plus 5 times 10 and 6 times 1. Now we can also write 100 as using the scientific notation, which basically is the same as 10 to the 2, and or 10 squared. Now, number 10 is the same as 10 to the 1, and the number 1 is 10 to the 0. So every number can be written as an expanded form. Let's take a look at another example. Let's say it's a 5069. Okay. Now, so in this case, this is a ones position. This is tens position. And this is hundreds position. And this is called thousands position. Now, in expanded form, we can write 5069 as 9 times 10 to the 0, because 9 is in ones position, and 6 times 10 to the 1, plus, now 0 is in hundreds position, because it's a number 0, so it's a 0 times 10 squared, and then 5 times 10 cubed, or 10 to the 3. Now that's the expanded form for the number 5069. So now let's introduce a new numeral system. It's the binary numeral system. Okay, we know that in the decimal numeral system, we use 10 symbols. Okay, we use 10 symbols, like a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 0 to 9, these are the 10 symbols in the decimal numeral system. Okay, so in the decimal numeral system, we know that we can count the number from 0 to 9, but if we want to count a number which is 1 bigger than 9, so in that case, we're going to actually add 1 to 9. So since 9 is the biggest number, so we cannot introduce any more symbols. So then we reset the ones position to 0, and then we create a new placeholder called tens position. Okay, so we actually write number 10 as a 1, 0. So that's tens position. Okay, and this is called a ones position. Now, the binary numeral system allows only 2 numbers, 2 symbols, 0 and 1. So that means once you count 0, count 1, Now, if we continue to count, if we want to count 2, then we cannot introduce a new symbol, like in this case. So what we're going to do, we're going to do the similar things, just like the decimal numeral system. So we're going to reset the ones position to 0, and then we're going to add a new position and put 1 in that new position. Since we add a new position after we reach number 2 instead of number 10. So then we call this 2's position. And this is also called a 1's position. Now we can continue to count, right? So 1, 0, and the next one is 1, 1. So because the 1's position is 0 with 0, we can introduce the number from 0 to 1. And that represents number 3. Okay. Now, if we want to add 1 more, okay, so then we find out there's a 1 in 1's position, so we cannot introduce any new symbols. So we reset the 1's position to 0. So we're supposed to add 1 to 2's position, right? Now we find out there's already a 1 in 2's position. So we end up like adding 1 to 1. So we're running out of position again. So then in this case, we can reset 2's position to 0, and then add another position on the left and add a 1 to it. Now that position is called 4th position, because when we reach the 3 and we want to add more, but we run out of position. So positions, so we add another position. It's called a 4th position. So this is how we're going to count the binary numbers. So we can count as 1, 0, 1, 1, 0, and 1, 1, and then 1, 0, 0, and then we can continue to count, right? So it's 1, 1, 0, 1. And then when we add 1 more, then we reset the 1's position to 0, add a 1 to the 2's position, 1, that's the next number, and a 1, 1, 1. Now, so this number is associated with 0, 1, 2, 3, 4, 5, 6, and 7. Now, if we want to add 1 more, then we need to reset 1's position to 0 and add a 1 to the 2's position. Now, since 2's position is already 1, so we're going to reset the 2's position to 0 and add a 1 to the 4th position. Now, again, 4th position is 0, is 1, so we're going to reset 4th position to 0 and add another position on the left, and that's called 8th position. Okay, that represents number 8. Now, let's take a look at another example. 1101 for the binary number. Okay, now remember, for binary number, the position of each digital in the binary number is also associated with a quantity. Unlike the decimal numeral system, then the quantity is actually 10. But in binary numeral system, the quantity is 2. So that means each quantity is twice the quantity of its right. Now, look at this case. Okay, so this is actually 1's position. And now we know that next one is not a 10th position, but it's 2's position now, because we use the binary system, right? That's 4th position, and that's 8th position. Now, if we have any number on the next position, what is this? Yes, that's 16th position. Okay. So we can also write the binary number as a expanded form. So that means we can separate the numbers in each position. Okay. So for this number 1 in 1's position, we can write it as 1 times 1. Now for this number 0 in 2's position, we can write it 0 times 2, right? And that one represents 4's position, so it's 1 times 4. And that one is in 8's position, so they're going to represent 1 times, they're going to be written as 1 times 8. Now also we can use the scientific notation. Now since it's binary numeral system, so the number can be written as the power of 2. So for 8 it's 2 to the 3, 2 cubed. For 4 it's 2 square, and for 2 it's 2 to the 1, and this 1 is 2 to the 0. Now this is very similar to the expanded form of the decimal number, right? For the decimal number, you can write as power of 10, but for the binary number, we can write as power of 2. Now in previous slide, we just talked about the expanded form or expanded notation for a binary number. Now we find out that this expanded notation can be used to convert a binary representation of a number into a decimal value. Now let's see how we can do this. Remember, this is a binary number. This is an expanded form. Now, if we simply add each of the number, we will actually get a decimal value. So, for example, this one, 1 times 2 to the 3, that's actually number 8, right? Now 1 times 2 square, that's actually number 4. And the 0 times 2 to the 1, actually that's 0, right? Because 0 times anything is 0. Now 1 times 2 to the 0, that's 1 times 1, which is 1. Now, so if we add these number 8, 4, 0, and there's 1, you will actually get the number 13. Okay, so that's the decimal value for this binary representation. So in this diagram, we just give you some kind of explanation how we going to convert this binary number into a decimal value. Okay, so this 1 represents 1's position, that's 2's position, 4th position, and 8th position. So this is 1 times 1 for 1's position. For 2's position, it's 0 times 2. 4th position, 1 times 4. 8th position, 1 times 8. So we got a 1, 0, 4, 8. Now we add these together, we get a 13. Okay. So we actually provide a way of converting a binary representation into a decimal value. Now the next question we have is, if you're given a decimal number, can we actually convert into a binary representation? That's an interesting question, right? Now the answer is yes. And actually there are 2 ways to do so. One is called comparison with power of 2. The other one is division by 2. So now let's take a look at the first approach, the comparison with power of 2. So now first we use the example of finding a binary representation of the value 89, the decimal value 89. Okay, so let's see, we have a number 89. So the idea of comparison with power of 2 is, first we're going to find the largest possible power of 2. Largest possible power of 2 that is less than 89. Okay, now let's take a look. So I think 1 is power of 2, right? It's a 2 to the 0. Now 2 is power of 2, right? It's power 2 to the 1. And the 4 is power of 2, right? 8 is a power of 2. Now 16 is a power of 2 because that's 2 to the 0, 2 to the 1, 2 to the 2, or 2 square, 2 cube, and 2 to the 4th. Now what about 32? So that's 2 to the 5. So we just see that we just simply need to double the number. So 2, 4, 8, 16, 32, and then the next number is 64, and then we double the 32, so that's 2 to the 6, right? Now what's the next one? Next one, we double the 64, that's 128. That's 2 to the 7. Now the first step is finding the largest possible power of 2 that is less than 89. So these are all less than 89, right? But the 64 is the largest power of 2 that is less than 89. So then we can write 89 as 64 plus, what is the number? Okay, subtraction, 89 minus 64, that's 25. Okay, so we can write 89 as 64 plus 29. That's one step. And then we just repeat the same process for 29. So we're going to find the largest possible power of 2 that is less than 29. Okay, so what is this number? Just look at this top one. We find out, okay, 32 is bigger than 25, but 16 is a power of 2, right? Which is less than 25. So then we can write 89 as 64 plus, and then we split 29 into 16 plus, what is the next number? 9, right? So we split 29 into 16 plus 9. And then we repeat the same process. So we have 64 plus 16 plus, now we find the largest possible power of 2 that is less than 9. So which is 8, right? So we can write 9 as 8 plus 1. Okay. So we can continue to do that, right? So until we basically convert 89 into the sum of the power of 2's, right? Powers of 2. So then we convert this. What is 64? It's a 2 to the 6. Now 16 is 2 to the 4 plus 2 to the 3 plus 2 to the 0. Now, so we have some kind of power of 2 missing, right? So if we want to make a complete list, we're supposed to have like a 2 to the 6, and the next plus 2 to the 5, 2 to the 4, 2 to the 3, and 2 square, and 2, and then 1. So this term is missing, right? This is also missing. This is missing. This is missing. Is it right? 2 to 6. 2 to, oh, sorry. 2 to the 3 is not missing. So it's there. So these 3 terms are missing, right? But that's fine. So we can write 89 as the sum of the power of 2. So 2 to the 6, which is not missing, then we can write as 1 times 2 to the 6. Now, for the second term, 2 to the 5, which is missing, then we can write as 0 times 2 to the 5, right? And then plus 1 times 2 to the 4, which is still there, And 2 to the 3, which is 2 cubed, is also missing. Then we can say it's 0 times 2 to the 3 plus 0 times 2 to the 2, which is 2 squared, right? And then plus 0 times 2 to the 1 and plus 1 times 1, which is 2 to the 0, right? So we can actually write 89 in terms of the sum of the power of 2. So this is actually what we got. So here's the number 89. So we just keep the same process and write all the 89 as the sum of powers of 2. So then we just actually add the missing part. Okay, so the missing part is actually the term that multiplied by 0. Okay, so now we can actually write 89 as the expanded form. Now, what is the binary representation for 89? Remember, that's the expanded form, right? And then each number, here I use the white color. So that number, each number represent the binary digitals. Okay. So we finally obtain the binary equivalence of 89 as this. So it's a 1, 0, 1, 0, 1, 1, 0, 0, 1. So it's 1, 0, 1, 1, 0, 0, 1. So that's the binary representation of 89. This is actually called a comparison with power of 2. Okay. So with the comparison with power of 2, we can always convert a decimal value into the binary representation. That's not a problem. However, we find out that if the decimal number is very big, then it's not easy to use the comparison with the power of 2, because we have to find the largest power of 2, which is smaller than the number. So this is not easy. So here we're going to introduce another approach. It's called division by 2. Now here are the steps for the division by 2. Now if we have a decimal value or decimal number, then step 1, we're going to divide this value by 2 and record the remainder. Okay. So, and then in step 2, so if the quotient of this division is not 0, so then we're going to continue to divide the nearest quotient by 2 and record the remainder. Okay, we're going to continue to do this. Once the quotient of 0 is obtained, then we then go to the step 3. Now step 3, we're going to record, all the remainders in certain order. So the binary representation is obtained by listing the remainders from right, remember the order, from the right to the left, in order they were recorded in step 1 and step 2. So let's take a look at the example. Okay, so let's say we want to actually convert a decimal number 13 into binary representation. Now let's do this. Step number 1, we're going to divide 13 by 2, right? And then we're going to continue to divide the quotient by 2 and repeat this process. So what we're going to do is we're going to start from the bottom. You will find out why we want to do this. Okay, so let's say step number 1, we divide the decimal value, which is 13, by 2, right? So what is the quotient? 6 or 7? 7 is too big, right? So we put a 6. 2 times 6, which is 12, and that's 1. So we record remainder. Okay, remember we're going to record that remainder. So now we got a quotient 6. So we divide, that's step 2. So the quotient 6 is not 0, right? So we divide the nearest quotient, which is 6, by 2. And then we got a quotient 3. And 2 times 3, that's 6. 6 subtract 6, that's remainder 0. So that's the second remainder. So now remember, we just record the remainder. Okay. Now we got a new quotient 3. So divide 3 by 2. So we got a quotient 1. 1 times 2 is 2. 3 minus 2 is 1. So record the remainder 1. And the next one gonna be 1. That's the nearest quotient. 1 divided by 2. So you got a quotient 0 because you cannot put 1. 1 times 2 is 2. 2 is bigger than 1. So you put the quotient 0. And 0 times 2, you got a 0. 1 minus 0, that's 1. So that's another remainder. Now we got the quotient 0, right? So once the quotient of 0 is obtained, go to step 3. Now, what the step 3 gonna do? So we're gonna actually list the remainders from right to left in the order they were recorded. Okay, so this one is recorded first, right? This one is recorded second. This one is recorded third. This one is recorded the last. Okay, so the first recorded remainder will be put on the right. Okay, so that's gonna be right 1, and then the second recorded remainder gonna be put next from right to the left, right? And the third one recorded here, and the fourth one here. So the number 13 can be recorded, as 1101. So that's the binary representation for the decimal value 13. Now here is another example. Now this time we're going to look at the number 89. It's kind of big number, right? It's not really that big, but it's, if we try to actually calculate it by hand, it's still a kind of big. So let's just do this. Okay, so we have 89. So what we're gonna do is we're gonna start from the bottom. So we have to be careful because we need to write the number small so we can squeeze everything in one page. 89 divided by 2. So we got the quotient 4. 2 times 4, that's 8, 9, and the 2 times 4, that's 8, that's 1. So we got a quotient, we got a remainder 1, right? Okay, so that one, that's the first remainder, so we're going to put on the right. So that the quotient is 44. So then we divide 44 by 2. So we find out the quotient is going to be 22, right? 2 times 2 is 4. 2 times 2 is 4. And the remainder is 0. So then 22 divided by 2, that's the nearest quotient. And then we got a 111, right? So that's the remainder is 0. So now 11 divided by 2, 11 is the nearest quotient. And then we got 5. 2 times 5, that's 10. So we got a quotient of 1. Oh no, quotient of 5 and remainder 1, right? And then divide 5 by 2, that's the nearest quotient. And then we got a 2. 2 times 2 is 4. Now you got the remainder 1 and a quotient of 2, right? Now, So then divide 2 by 2. So we got a 1. 1 times 2 is 2. And the remainder is 0, right? And then we got a quotient of 1. And then we divide 1 by 2. That you got a quotient of 0. 2 times 0. That's 0. And remainder 1. Okay. So now we repeat this process. And we got total of 1, 2, 3, 4, 5, 6, 7. 7 remainders. Now, based on the step 3, we're going to actually, put the first remainder on the right. And then the second remainder, it's left, it's 0. Third remainder, 0. Fourth remainder, 1. 1. 0. And a 1. So we got the binary representation 1, 0, 1, 1, 0, 0, 1. So 89 is actually the binary representation for 89 is 1, 0, 1, 1, 0, 0, 1. Okay. It's very simple, right? So here's a summary of the previous example. Okay, so we have 80, we have 89, we have a number 89, decimal number 89, right? And then we do the division. 89 divided by 2, you got a 44, quotient 44, and then we got remainder 0, 1. And then we continue to do this division, and we record the remainder. Okay, so that's the number. So we got this. Okay, now this division is kind of awkward. It's not really convenient, right? So here on the right, we use the another form called a short division by 2. So this is just actually a different notation. It's a math notation. So we can go from the top. So 89 divided by 2, and you record the quotient and record the remainder. And then 44 divided by 2, you record the quotient and record, and record the remainder. So we're just doing this using the short division format, and then we can get the same result. Now it's just a different, division form. So it's a short division. It's you're gonna save some space, and it's easier to understand. So we now know that for every binary numbers, we can convert into a decimal value, and also for a decimal value, we can convert into the binary representation. Now this conversion is 1-to-1. So why we want to do this? Because in our daily life, we use the decimal numbers before we get used to it. Now, but the computer system use the binary numbers. Okay, remember, computer systems actually using the electronic device, which is really designed to process the binary numbers. So that's the reason why we want to study the binary numeral system. So once we know how to represent a binary numbers, the next one we want to know is how can we perform the arithmetic operations like a binary addition. Okay, so is the procedure for binary addition is exactly the same as that of decimal, but you need to remember that the binary number is base 2 numeral system instead of 10. Okay, so actually the addition for 2 binary numbers can be done by repeatedly applying the single digital additions. This is just the same as the decimal. Now let's take a look at the example. Okay, so if we want to add two numbers, right? So let's say 38 plus 15. So we can actually add these two numbers by repeatedly applying the single digit addition. So we first start the single digital in ones position, right? Single digitals in ones position. So we add 8 and 5. Okay, so 8 times plus 5. So this is actually 13, right? It's 13. So in the single digital, in ones position, it's 3. Okay. Since it's 13, there's a 1 in the tens position. So then we can actually carry this tens position, carry this 1 to the next position. Okay. So then the next step is to add two single digital in tens positions. So we add a 3 and a 1, right? So it's 4. However, we know that there's a number 1 carried over from one's position, right? So 3 plus 1 is 4, and then we need to add that 1 which was carried over from one's position. So we got 5. Okay. So that's the addition for the actual decimal numbers. Now for the binary number, it's very similar. Okay. So we're gonna add the single digitals, you know. Okay, we're gonna add the single digital. Okay, so starting from the ones position. So let's take a look at the addition like this. So we have a 1, 0, 1, and we're gonna add another number. Okay, 1, 0, 1, 1. So the other number is 0, 1, 1. Okay, we want to add these two numbers. So we're gonna start from the ones position, right? So we add a 0, 1, and a 0. So that's 1. Okay, that's 1. There's no carryover number. Now here, 1 plus 1, so we got a 2, right? Now based on the binary addition, 1 plus 1 is 2, but a 2, the binary representation for 2 is 1, 0. So now we're going to actually 1 plus 1, you got the 0 in that position, and then we're going to carry a 1 to the next position, right? So then look at the fourth position. So it's a 0 plus 1, then you got a 1. But don't remember, you have a 1 that carried over from the previous position. So 0 plus 1, you got a 1, then plus another 1, so you got 2. Again, it's 1, 0. So we got to put 0 here and carry a 1 to the next position. Okay, so in the next position, which is 8th position, so you have a 1 for the first number, and you have nothing for the second number. So that means 1 plus nothing, it's 1, right? But remember, we have a 1 which was carried over from the previous position. So now you have a 1 plus 1. So you got a 0, 1 plus that 1. You got a 0, and a carry over to the next position. So it's 1, 0, 0, 0, 1. Okay, that's binary addition. So during the binary addition, we're going to perform the single digital additions. Now first from the ones position, and then from the twos position, from the fourth position, from the eighth position, just like the decimal case. You're from ones position, tens position, and hundreds position, right? Now, if there's any number, when you add in any position, then if you actually will carry over a number, and that number will be carried over to the next position. And don't forget, when you actually perform the addition in the next position, you have to add that number that carried over from the previous position. Don't forget this. Now let's take a look at another binary addition. So in this example, we have two numbers, 1, 1, 1, 0, 1, 0, and then the other number is 1, 1, 0, 1, 1. So we need to line up the numbers on the same position, right? So let's start from the ones position. Okay. So we have a 0 plus 1, then we got a 1. So there's nothing to carry over to the next position, right? And then we add the number in the twos position, the single digit in the twos position. So 1 plus 1, you got a 1, a 0, and you're going to carry over a 1 to the next position. Remember, 1 plus 1 is 1, 0. So you record a 0 in the current position and carry a 1 to the next position. So then you have a 0 plus 0 in the next position, in fourth position. 0 plus 0, that's 0, but don't forget to add the 1. Add that 1. So you got a 1. And there's no carryover, right? That's good. So then, next one is 8th position. So you got a 1 plus 1, so you got a 0, and you're going to carry 1 to the next position. Okay? So, the next position, which is 16th position. So you got a 1 plus 1, so that's 0, right? And then you're going to carry 1 to the next position. But remember, 1 plus 1 is 1, 0. And then you need to add the position carried over from the previous position. So then 1 plus 1, 0 plus 1, that's you 1. Then carry a 1 to the next position. Okay. So it's kind of tricky. You basically add three ones, right? So add a 3 when you got a 3. 3 is 1, 1, right? So you got a 1 and carry a 1 to the next position. Now here in the 32th position, so 1 over here plus nothing at the bottom, so you got a 1. And don't forget the 1 carried over from the previous position. So you got a 1 plus 1, so you got a 0. And carry a 1 to the next position. So you got a 1. So the final result is 1, 0, 1, 0, 1, 0, 1. So these are the ones that carried over from the previous position. So okay, here's the final result for the previous example. Okay, so we actually also should these are the carryover numbers from the previous position. And actually, you should also have a carryover number over here, right? So that's the final result. So let's look at the binary subtraction. So we're not going to spend much time on binary subtraction because later on we're going to find out we're going to introduce a new type of binary notation so we can actually avoid the binary subtraction. But first, let's take a look at binary subtraction. So we're going to look at the example here. So there are two numbers, 1, 1, 1, 0, 1, 1, 0, 1, 1. So the binary subtraction is very similar to the binary addition. So we're going to start from the ones position and then twos position, fourth position. Okay, now before we do this, let's take a look at the subtractions for the decimal numbers. Okay, let's look at this 2, 3, 4 and minus 5, 3. Okay, so the top number is bigger than the bottom number, so you can do the subtraction. So we're also going to do the single digit subtraction starting from the ones position. So in the ones position, 4, top one is 4, bottom one is 3, so 4 minus 3, that's 1. Great. Now, the next position, the tens position. So top one is 3, bottom one is 5. However, we know the top number is bigger than the bottom number. So even though in the tens position, the top number is smaller than the bottom number, but we can borrow a number from the next position. So the next position, we have 2, right? So if the current position want to borrow a 1 from the next position, then we can borrow 1 from the next position, so leaving, so the next position gonna subtract 1. So the other 1 is borrowed by the current position. Now remember, in the decimal, every 1 in the next position represents 10 in the current position, right? So the 1 borrowed from the hundredths position, it's actually represented 10 in tens position. So this one going to be counted as 10 over here, right? So now in this tens position, we are basically have 10 plus 3, then minus 5, because we borrowed 10 from the previous position. So we borrowed 1 from the previous position, but it's counted as 10 in the current position. So it's 10 plus 3 minus 5, and we got 8. So now after we finish the tens position, then we're going to do the subtraction for the hundredths position. But in the hundred position, the top number is 1, right? Because 1 is borrowed from the tens position. So the top one is 1, the bottom one is nothing. So 1 subtracted nothing, that's 1. Okay, so that's the final result. Now, for the binary subtraction, it is very similar. So we're going to start from ones position. So the top 1 minus the bottom 1, so 1. So 1 minus 1, that's 0. Everyone is happy. Now, for the twos position, the top 1 is 0 and bottom 1 is 1. So in that case, we need to borrow a number from the next position. Okay, so the next position has 1, so we can borrow that 1, so making 0 here, but that 1 going to be used here in the current position. Now remember, every number in the next position will be counted as 2 for the binary number, right? Will be counted as 2 in the current position. So that number will be counted as 1, 0. It's not a 10 because it's binary number. So the 1, 0 means 2. So here, when we do the subtraction, so the top number will be 10, 1, 0 plus 0. So it's still 1, 0. That's 2. Then minus 1. So it's 2 minus 1. So you got a 1 here. Okay. And then once you complete the subtraction in twos position, then you're going to look at the fourth position. Now the fourth position, the top 1 is 0 now, because the 1 has been borrowed by the twos position. So it's 0 minus 0, that's 0. 1 minus 1, that's 0. 1 minus nothing, that's 1 actually. So that's the final result. So that's a really simple example. Now sometimes, the subtraction will be a little bit more complicated. So let's take a look at this one. So it's a 1, 0, 0, 0, 1. And then 1, 1, 0. Let's take a look at this one. So we start from twos position. So 1 minus 0, that's 1, right? But now in twos position, it's a 0, top 1, 0, minus 1. So the top 1 is smaller than the bottom 1. So we just want to borrow a 1 from next position, right? And then we find out the next position is 0 as well. So there's nothing to borrow from. So then the next position say, okay, I'm 0. I have nothing to give you. So I'm going to borrow from my next position. Okay, but the next position is still 0. So there's nothing to borrow from. So then the next position I'm going to borrow from its next position, which is 1, right? So then you can borrow 1 from here, so making the current that position 0. So then the one just borrowed from next position over here, it becomes 10. Oh no, I'm sorry, it's not 10, it's 1 0, which is only 2. Okay, 1 0 it means 2 in binary numbers. Okay, now so this 1 here represented 2 in the previous position. Now then in this 2, I'm only use 1. I only just carry 1 to the previous position. So I'm going to split that 2 into 1 plus 1 and leaving 1 here. And the other one going to be borrowed by the previous position. You see that one? It's a little messy. So again, so this position actually got a 2, but the previous position only requests for 1, right? I only just want to borrow 1. So then I'm going to split that 2 into 1 plus 1. So then 1 is actually positioned here. The other one will be borrowed by the previous position. And that one will be interpreted as 10, 1 0. I'm sorry, not 10. Over here. So now I have a 1 0 plus 1, that's 1 0, and minus 1, that's 1, right? 1 0 is 2. Interpret as the value 2. So 2 minus 1, that's 1. Okay. And then over here, in this position, remember the top one is 1, right? So it's borrowed from the previous position as a 2, and the 1 is actually given to the next previous position. Okay, the other one is actually stays here. So this one is a 1 and bottom one is 1. So 1 minus 1, that's 0. And then this one is also, this position is also becomes 1, right? Because it borrowed from the next position. And so 1 stays here, the other one is, give to the previous position. So that's 1. 1 minus nothing, that's still 1. And then this position is 0. So there's nothing in here. Okay, 0 minus 0, that's nothing. So the final result is this. So this is a little bit tricky because you have to actually borrow from the previous one. If the previous one has nothing, you have to borrow from the previous one again. So, but the good news is we don't need to deal with binary subtraction in computer science. Okay, so that's the end of module 4.